In this video, we are going to discuss about the analysis of variance, and the topic is to focus on the one-way analysis of variance, or ANOVA. The goal is to use the hypothesis testing technique to compare the means of 3 or more populations. In the past, we only focus on 1 mean, 2 means, but not 3, not 4, not 5, and so on. But in this section, we are going to compare the means of 3 or more populations. Now let's take a look at the example or problem that we have here. A pharmaceutical company is analyzing the effectiveness of 3 types of painkillers and wants to determine whether there is a difference in the mean length of time it takes the 3 medications to provide relief. Now, one independent variable is being studied in this problem, and that's why we call this the one-way analysis of variance. And we are trying to compare the mean length of time of 3 painkillers using the analysis of variance. So they have 3 different types of the painkillers, and therefore we are using the one-way analysis of variance, or ANOVA, to compare the 3 means of the populations together. Now it's very similar to in the last few chapters. We are still using the null hypothesis and the alternative hypothesis. H0 is the null hypothesis. So for the null hypothesis, we are assuming that all the population means they are equal. In this case, we are talking about the mean, so we assume that they are all equal. mu1 equal mu2 equal mu3 mu4, they are all equal to k. K is the total number of the population that we have in the problem. And then H alpha, this is the alternative hypothesis. Sometimes we call this H1. Some textbook they are using H alpha. For the alternative hypothesis, we assume that at least one mean is different from the others. So one of the value, maybe mu1 is different from the rest of the value, or mu3 is different from the rest of the value. And when we are rejecting the null hypothesis, which is this one, in the one-way ANOVA, we are making the conclusion that at least one of the means is different from the others, because we are rejecting the null hypothesis. That means we say that they are not all equal to each other, and therefore at least one of them should be different from the others. There are a few requirements for us to check before we can apply the one-way ANOVA. The first requirement is that each of the case samples must be randomly selected from a normal or approximately normal populations. Now we are required to have at least 3 of them, 3 populations, because we are comparing 3 or more means together. So K needs to be at least equal to 3 here. And each sample must be randomly selected from a normal population. The samples must be independent of each other. So the first sample is independent of the second one and the third one, and so on. And each population must have the same variance. Now, if these conditions are met, then the sampling distribution for the test is approximately equal to the F distribution, and we are using the F, the test statistic of the F distribution to be MSB divided by MSW. This is just the ratio of the variance between the sample. MSB is the variance between the samples, measures the differences related to the treatment given to each sample. And sometimes we call this the mean square between the samples. And then MSW is the variance within the samples, measures the differences related to the entries within the same sample, and they usually due to the sampling error. And sometimes we call this the mean square within. So the test statistic F here is the ratio of the variance between the samples divided by the variance within the samples. So make sure that we follow the test statistic here. And the degrees of freedom, we have two different types of degree of freedom. The degrees of freedom for the numerator and the degrees of freedom for the denominator. Degree of freedom for the numerator is denoted by dfn. This is equal to k subtract 1. K is the number of the samples that we have. And the degree of freedom for the denominator is equal to n minus k. The big N here is the sum of all the sample size that we have. And then minus k, which is the number of the samples. So those are the requirements that we need to check before we can apply the one-way analysis of variance. And if there is little or no difference between the means, then the mean square between will be approximately equal to the mean square within, if there's little or no difference between the means. And therefore the test statistic would be around 1, because the numerator and the denominator, they are approximately equal, and therefore if you take the ratio, you should get around 1. So if the test statistics is around 1, or the values of f close to 1, is suggesting that you should fail to reject the null hypothesis. So if it is around 1, so you should fail to reject the null hypothesis, or H0. Okay. However, if one of the means differs significantly from the others, so maybe mu1 is very different from mu2 or mu3, one of them differs significantly from the other, then the mean square between will be greater than the mean square within, and the test statistic will be bigger than 1, because the numerator now has the bigger value than the denominator, and therefore if you take the ratio, you should get something bigger than 1. So the values of f is significantly greater than 1, suggesting that you should reject the null hypothesis. So in this case, you are going to reject the null hypothesis, or H0. So all the one-way analysis of variance, or ANOVA tests, they are all the right tail tests. That is, if the test statistics is greater than the critical value, then H0 will be rejected, or we rejecting the H0. This is the right tail only. Okay. Now, those are the general steps for finding the test statistic for any one-way ANOVA. The first step is we are going to find the mean and the variance for each sample. So we are using x bar I, the mean, the variance, and then we are also find the mean for all the entries in all the samples. And we sometimes call this the range mean, or the mean with the double bar. This is the summation of all the x divided by the big N. And then find the sum of squares between the samples. Sum of square between the samples using this formula, and find the sum of square within the samples using this formula, and then find the variance between the samples, or the mean square between, and that is going to be the SSB, the sum of squares between the sample, divided by the degree of freedom of the numerator. And for the variance within the samples, again we are using the sum of squares within the sample divided by the degree of freedom of the denominator, or n minus k. And then finally, when we get m as b and m as w, we take the ratio and we get the test statistics. And make sure that we have to verify that the samples are random and independent. The populations have normal distributions and the population variances are equal. And then now we need to identify the claim. Again, we need to find H0 and H alpha, or the alternative hypothesis. And then we're going to specify the level of significant alpha. This is usually given for you. And then determine the degree of freedom, and then determine the critical value. We can use that from the table 7. I include here. So we have table 7, the F distributions with a different value of alpha. And this is the degree of freedom for the denominator. This is the degree of freedom for the numerator, horizontally and vertically here. And then make sure that we follow all the steps that we have here, so that we can find the ratio or the test statistic. And after that, we're going to make the decision if the F statistic is inside the rejection region. Then we reject that null hypothesis. If not, then we fail to reject. And then, of course, at the end, we need to interpret the decisions in the context of the original claim. Okay, those are the long processes here. But we have one example that we can go over of the each of the steps that we just discussed, and hopefully it will make more sense after we finish the example. Okay, this is a good example here. A medical researcher wants to determine whether there is a difference in the mean length of time it takes 3 types of pain relievers to provide relief from the headache pain. Several headache sufferers are randomly selected and given one of the 3 medications. Each headache sufferer records the time in minutes it takes the medication to begin working. The results are shown in the table below here. At the alpha level of 0.01, can you conclude that at least one mean time is different from the others? Assuming that each population of the relief times is normally distributed and that the population variances are equal. So we verify that the samples are randomly selected. Yes, because several headache sufferers are randomly selected. And they are all independent, right? And then we also given the fact that those came from the normal distribution, and also the population variances are equal. So we meet all the requirements in order to use the OneWay ANOVA. And in this case, we have what? We have 3 different medications. So we are comparing 3 different means, and therefore we have to use the OneWay ANOVA. Alright, so the first medication, we have 1, 2, 3, 4. So in this case, we have 4 samples. The second one, we have 1, 2, 3, 4, 5. So I call this N2 to be 5. And the last one, we have 1, 2, 3, 4. I call this N3 equal 4. We also need to find the mean for the first one. So I add all of them together, 12, 15, 17, and then again 12. We add them together, which is 56, and we divide by 4. So the mean of the first one is 14. And similarly, we do the same thing for the mean of the second one. We add all of them together, we get 85 over 5. And that is going to be equal to 7 because we have 5 of them. And lastly, we are going to find the mean of this medication number 3. We add all of them together, which is 66, and then we divide by 4 of them, and we get 16.5. And we also need to find the variance for each of them. Alright, so variance S1 square. We also need to find variance of this one too. And we also need to find the variance of the last one too. So you can use the calculator to find the variance for each of them. And that should give you 6 here, 8.5 here, and 7 here. Now let's pick one of them and let's try to do it by hand to find the variance for the first medication right here. So SI, we have the formula SI square is going to be equal to the summation of X minus XI. This is the formula to find the variance over N minus 1. Now the X bar, this is the mean, we got at 14. And X is just each of the samples right here. Now this is the summation notation. So I'm going to take what? I'm going to take the first point 12. Right. Let me move it all the way here so we have more spaces. So 12 minus the mean and then square. Okay. And then we're gonna add to this is the summation. The next point is 15 minus the mean, which is 14, and then square. And then add to what? Add to 17 minus 14 square. And then add to the last point, 12 minus 14 square. And then we take everything here, we divide by N minus 1, N is 4, so 4 minus 1. Let's try this calculation right here. Alright, so we have 12 minus 14 square plus 15 minus 14 square plus 17 minus 14 square, and the last point 12 minus 14 and then all the way square. And then now we divide by 4 minus 1, which is 3, and that's going to give me 6 right here. So that's how we use the formula by hand, and doing similar steps, you should get these two values here. Okay, so after we find the mean, these variances for each of the sample, then we are going to state the null and the alternative hypothesis. Okay. Alright, so for the null hypothesis, we always assume that all the means they are equal. So I assume that mu1, the mean of the medication 1, equal to the mu2, the mean of the medication 2, and also equal to mu3. This is the assumptions we make. And now mu the alternative hypothesis, this is where we assume that at least one mean is different from the other. So we are going to write at least one mean is different from the other. And in this case, this is also the claim that we have in the problem, because the problem asks you, can you conclude that at least one mean time is different from the other? So this is exactly what we have right here for the alternative hypothesis. This is the claim. Now we have 1, 2, 3. So we have 3 medication. So your K value, the sample is 3. And therefore, from here, I can go ahead and I can find the degree of freedom for the numerator. Then that's going to be equal to K minus 1. Or it's just 3 minus 1 equal 2. And then for the degree of freedom, for the denominator, we are going to take the big N minus K. Now the big N is found by what? By summing all the sample size. And 1 and 2 and 3 we have here. and that's gonna give me 13 right here, right? 4, 5, and 4, this is 13. So 13 minus 3, that's gonna give me 10. Okay. Alright, so we have everything. We have alpha in this here as well. Alpha is given as 0.01. 0.01. So it looks like now we have almost all the things that we need in order to move on to the next step. The next step is to look for the critical value. Okay. So with the alpha to be 0.01 and with alpha to be 0.01 and the degree of freedom for the numerator and the denominator, we are going to find the critical value f naught. And how do I find that? Well, I have the alpha to be 0.01, degree of freedom or for the numerator is 2 and denominator is 10. So 0.01 is, let's look for the table of 0.01, which is right here. And the degree of freedom for the denominator we got was 10, right? 10, so it's right here. And the numerator we got 2, so 2 is right here, and that's gonna give me this value 7.56. So 7.56 is the critical value. So after we have alpha degree of freedom, we are going to get the critical value, so 7.56. This is what we will use later on to compare the test statistics. If the test statistic is bigger than this value, that means we are inside the rejection region, and therefore we need to reject the null hypothesis. But before that, we have to do all the stuff. The next step is we need to find the x double bar. Right, this is the rand mean x double bar, and this is the summation of the x divided by the big N. We have all the x, the value, the x here, the sum of all the x, the sum of all the value here, here, and here. The sum of all the medication 1 samples was 56, 85, and 66. So we are going to add them. 56, 85, and 66, and we are going to divide by n, it's 13 we found earlier here, and that's going to give me 15.92. And then we are going to need to find the mean. We are going to find the mean square between, and that is going to be equal to sum of square between divided by the degree of freedom on the numerator. And for the sum of square between, that's going to be equal to the summation of ni xi, the mean, minus the rand mean square, and divide by k minus 1. Okay, so now let's see how we are going to find this long expression right here. Alright, so we know that we are going to need the sum, because this is the summation. Ni, your n is right here, 4, 5, and 4. So the first one is 4, right? And then the mean of the first medication, the mean is 14. so 14, minus the rand means 15.92 square, and then add to the next one, and 2 is going to be equal to 5. And next to the mean of the second medication, 17. And then minus the rand means, which were the same thing as before. And then lastly, we have 4 of them, and the mean was 16.5 minus the rand mean square, and then all over k minus 1, and this is k is 3 minus 1, and if you do all the calculation here correctly, you should get 10.9616. This is the mean squares between is equal to the sum of square between divided by the degree of freedom for the numerator. Using the similar step, we can also find the MSW, the mean square within, and this is SSW. So MSB is SSB, MSW is SSW. The sum of square within divided by the degree of freedom of the denominator. Okay, so we are using a very similar formula here, but then on the numerator, the formula is a little bit different. We are taking the sum of ni minus 1 multiplied with si square, and then all divided by n minus k. Again, ni is the number right here, n1, n2, n3. So the first one, ni, the first one is medication 1, ni is n1 is equal to 4. So 4 minus 1. Si is the variance, ni square, right? Ni square is the variance of the medication 1 of these 4 number, which is 6. So we multiply by 6, and then this is the summation. So we add to ni for the second one is 5. Again, 5 minus 1, and then multiply by the variance of the second one is 8.5. And then the same thing to the last one. It's going to be 4 minus 1 multiplied by 7, and all divided by the big N here is 13. The sum of all the n's together, 4 plus 5 plus 4, that's going to be 13. So 13 minus k, we have 3 samples, 3 different medications, so minus 3. If you do all the calculation here, then you are going to get 7.3. After we get MSB and MSW, then we can go ahead and find the F statistics, and that is the ratio between MSB divided by MSW. Okay, so we got that. Then now we are taking the two number, right? Take the ratio between them. So I'm going to write down here. I'm going to find the F statistics. So MS between first divided by MSW, and we got these two values right here. So 10.9616 divided by 7.3, and that's gonna give me around 1.50. And we can graph the F statistic or F distribution, and from there we can see if we reject or we fail to reject. So remember, we start from 0, right, for the F distribution. So we 0, and you can just kind of wrap the curve, and just simply label 2, 4, 6, 8, and so on. Right? We know that our critical value F naught was 7.56. So 7.56 is below 8, so it's around here, right? 7.56 is right here. So the critical region is the one to the right of that number here. This is the critical rejection region. However, our F statistics is 1.50, so that is all the way down here, right? 1.50 is around here. So 1.50 is our F statistic, and this is way below the critical value, or this is of course outside the rejection region. Because this is outside the rejection region, it is not in the rejection region. You fail to reject the null hypothesis. So fail to reject the null hypothesis, or H naught. So we fail to reject H naught. That means mu1 should equal to mu2 and it should equal to mu3. And from there we can make the conclusion about the claim. So they ask you, can you conclude that at least one mean time is different from the others? Because we fail to reject the null hypothesis, therefore we don't have enough evidence to support the claim. There is not enough evidence at the 1% level of significance to conclude that there is a difference in the mean length of time it takes for the 3-band painkillers to provide relief from the headache pain. So we don't have enough evidence to support this claim. And finally, do not forget to write the conclusion. So let's write that in the complete sentence here. There is not enough evidence at the 1%, this is 0.01 level of significance to conclude that there is a difference in the mean length of time it takes for the 3 pain relievers to provide relief from the headache pain. Okay, so that's how we perform the OneWay ANOVA by hand. So of course it took a lot of time for all the calculation by hand, the mean square of between and mean square of the within, degree freedom, and so on. Now let's try to see if we can use the TR-84 and Excel and get the answer right way, quicker, and we don't have to perform a lot of the hand calculation here. First, let's try the TR-84. So we have the medication 1, 2, and 3. So the first thing is you need to enter all the samples of medication 1, 2, and 3 into the list of maybe L1, L2, and L3. So go to Start, Edit here, and on the list L1, you are going to enter 12, 15, 17, and 12. And then on the list L2, you are going to enter 16, 14, 21, 15, and 19. And then this, lastly, for medication 3, you are going to enter 14, 17, 20, and 15. So we need to first store all the data into the list L1, L2, and L3. And let's go out and then go to Start. You are going to use the test menu here, and then we are going to scroll down and we are going to choose the ANOVA, which is this option, the H1. Okay, this is analysis of variance ANOVA. And we store the data into L1, L2, and L3, and therefore you need to enter the input here as L1, L2, and L3. L1 is right here. This is the blue color, so you are going to use second. Hit this to get the L1, comma, L2, comma, L3. And then hit enter. And that will give you right away OneWay ANOVA. And you can see that your F statistics is given right here 1.50, which is what we got earlier. Now you can get it right away. And you can also get what? You can also get the real freedom 2, which is right here. We have it here, right here, and sum of square, the mean square, and so on. However, there's another important thing that you can get from the TI-84 is the p-value. So we got the p-value. The p-value in this case is 0.269. And we know that 0.269 is bigger than the alpha, which is 0.01. So when the p-value is bigger than this level of significant alpha, you fail to reject the null hypothesis. We only reject the null hypothesis when the p-value is less than the alpha or the level of significance. In this case, it's bigger than, so we fail to reject. So we still end up with the same conclusion right here. So we fail to reject the null hypothesis, or there's not enough evidence to support the alternative hypothesis. So either way, you still end up with the same thing from the p-value or from the critical value methods. You still get the same thing, the same conclusion. So that's how you use the TI-84. And lastly, we can also use Excel for this problem. Let's try that now. Okay, so for the Excel, the first thing is you are going to enter all the data in each column. So we label Med 1 stands for medication 1 and Med 2 for medication 2 and so on. And then we go ahead and we enter 12, 15, 17, and 12. And then the same thing to the second column for the second medication and so on. Now, in order to perform the ANOVA analysis, right, we go to a Data tab and then click on Data Analysis. And we are going to use the ANOVA single factor. This is OneWay ANOVA. Click OK. And for the input range, you are going to select all the value. Now, do not select the title, only the data. Okay? And we are rubric by the column. And then for the output range, you are going to place the answer into another place. Maybe we place them over here, right? So just click on the output range and just click random cells, maybe all the way down here, so that we can see the whole value over here. You can display the value using a new worksheet, but I think it's better to display together on the same sheet here is fine. Okay, and then now you are going to click OK, and you can see that they perform all the analysis and they place the answer right here, and you see that from the ANOVA, we also get the F statistic 1.50, and this is also consistent with what you got earlier. 1.50 is right here. And the p-value is also 0.269, and that is exactly the same thing as we got from the TI-84 to 0.269. And this is again bigger than alpha, so we fail to reject. We only reject when the p-value is less than alpha, which is 0.01 in this case. So using the Excel or using the TI-84, you can get to the conclusion right away. Otherwise, you have to go through all the steps here and still get the same answer, but you can do that by hand. Okay, so that is the conclusion of this video, which is the analysis of variance one way, and we learn how to use the TI-84 and also the Excel to perform the analysis.